Alright, section 3.2 is where we are in statistics, and that would be measures of variation. Last time was the measures of center. Now this is measures of variation. So I have two students here. Let's compare them. Okay, so let's look at their means and their medians. Alright, if you were to add up for student A all these numbers and then divide by 5, you would get that student A has an average of 90. So student A has a mean of 90. Now what would the median be for student A? Well, first of all, remember we got to put these numbers in order from least to greatest. And since this is an odd number, there are 5 numbers here, it's going to be the middle number. So our median is 90. Okay, that's student A. Student B, go ahead and look at these numbers. Student B has, if you find the mean of student B actually has a mean of 90. Alright, well if we put those numbers in order, 88, 88, 90, 91, 93, these are odd, so middle number, so it actually has a median of 90. Alright, well, who's the better student? Well, we can't tell because everything we've used so far says they're the same. Well, who is the more consistent student? That's the question. Who's the more consistent student? Well, look at number 1. Look at how the data is kind of spread out. 100, 90, all the way down to 70. But look at example 2, student 2. How this data is all grouped together right there around 90. Student B is actually more consistent. This is what we call variation. The variation in the data in student A is a lot more than the variation in the data in student B. Okay? So, one way we measure variation is with range. And you know what range is. Range is the maximum minus the minimum. Simple as that. The maximum observation minus the minimum gives us the range. Now, standard deviation is what we use to measure variation by indicating how far the average is, on average, how far observations are from the mean. So we know what the mean is, and then we judge how far the other observations are from the mean. That's what standard deviation does. Now, you've got 2 formulas for standard deviation. You've got the sample standard deviation that we have here. Now, I'm not going to work out an example with sample standard deviation. There's one in your book worked out for you. But the reason I'm not going to work this one out is because I like using the second one better. If you want to use this one, by all means, go ahead. Like I said, it's a more difficult version, in my opinion. And then here's an example with it if we were to work it out. But I like the computing formula. Now, how would we use the computing formula? Well, look at the data we have here. This is our student A data that we had from earlier. If I'm doing student A data, my X values here are 70, 90, 90, 100, 100. Okay. Now notice what I'm wanting. I'm wanting the sum of x squared and the sum of x squared. Okay. So what we need to do is figure out now what the sum of x sub I is. That would be adding all of these up. And we found earlier that it's 450. Well, let's look at x squared now. X squared would be 70 squared, which is going to give us our 4,900. We've got 90 squared, and we've got 100 squared, which is going to give us our 10,000. Okay, so add all this up, plus 8,100, plus 8,100, and add up all those values in that column, and that gives you 41,100. Now, what this right here, is the sum of the x's squared. Now, notice, we need also this value. Well, what is that? That is 450 squared. So what's the square of 450? Well, 450 squared, in your trusty calculator, is 202,500. All right, so we've got the sum of x sub I squared minus the sum of x sub I squared. Okay. Hopefully that makes sense in the difference in those two. So what we have here is we have the square root. Now we can start in our formula. The square root of 41,100, excuse me, minus 202,500 divided by n. How many do we have? We have 5. All over n minus 1. So 5 minus 1 would be 4. So 202,500 divided by 4 is 50,000. Excuse me, 202,500. I knew that didn't look right. Divided by 5 is 40,500. So what we actually have here is we have the square root of 41,100 minus 40,500 divided by 4, which is going to give us the square root of, now just subtract those out. That's 600 divided by 4. Okay, and so 600 divided by 4 is going to give us 150. Now, I didn't tell you how many decimals to use here, so we're just going to make this up on the fly. So find your approximation, the square root of 150. And I'm going to do one decimal place. That's 12.2. 12.2. So what that tells me is the standard deviation is 12.2 from the mean. That this data is standard deviated 12.2 units from the mean, basically. All right, so with our standard deviation, it allows us to see if they're relatively close together or not. Now, 12.2 tells me that those aren't relatively close together. Okay, you want your standard deviation to be close to 0. The closer it is to 0, the closer your data is together. Okay, and be careful not to round until the calculation's complete. Otherwise, you're going to have round off error. Never ever round until the very end. Now, I like the computing formula. That's what I like. By all means, if you want to try the other way, be my guest. As I said, there are tons of examples in the book. And I'm sure your instructor would be more than happy to provide you with an example if you wish to do it the other way. But the computing formula, in my opinion, my humble opinion, is going to be easier for you to work and understand. So keep that in mind as you're doing this. So on average, it's we are 12.2 from the mean. Okay, and notice how I said that. Keep in mind that 12.2 number because it's about to erase it. But notice how I said that. Measures variation by indicating on average how far observations are from the mean. So this is telling you on average they're 12.2 from the mean. So it's averaging that difference basically. On average, how far are we from the mean? So that's what standard deviation means there. And we can use it to tell, whose data is closer together, whose is not, who's a little more consistent. The main reason for standard deviation, in my mind, is who's more consistent. What data is grouped closer together, and what a better way to segue into this example. Look at these two data sets. I gave you the mean and standard deviation on the right hand side. This would be something good for you to practice. If you want to practice your computing formula, use these because I've given you the answer so you know what you should be coming up with. So this would be a good thing for you to practice. Hint, hint. I would go back and do that. Now, more variation. The more variation there is in the data set, the larger the standard deviation. So look at this group of numbers here. Look at this data set 1 and look at this group right here. Okay, notice we start at 40, end at 66, and all these numbers are fairly closely grouped together here. Now look at the second set. We have some extreme numbers here. I mean, look at 20 and 70. These numbers are more spread in the 30s. Only one of them in the 60s, and only two in the 50s, and only three in the 40s. They're not as grouped together as they are up here. Which is why, if you notice data set 1, look at the standard deviation for these two. Notice, the mean is exactly the same. This is why you can't always use mean with extreme values. Because notice, the mean for these two data sets is exactly the same. But notice, in data set 1, our numbers are more are packed more grouped in more of a group. And so they're more consistent. And that's why you see the smaller standard deviation versus the larger one. Now, almost all standard deviations in the data set lie within 3 standard deviations to either side of the mean. So in terms of standard deviations, a moment ago we had 12.2. So one standard deviation from the mean would be 12.2 on average. Another one might be 24.4 and so on. Okay, how many standard deviations are we from the mean? Okay, now for further explanation, there are more precise versions of the 3 standard deviation rule. You've got Chebyshev's rule and you've got the empirical rule. Now I'm not going to speak much on Chebyshev's rule. You can see it in front of you and you can read it, but empirical rule I will speak on because when we get to normal distributions, the empirical rule is going to come back to be one of our friends, because basically what the empirical rule says is if we have a normally distributed data set, if you have a bell-shaped curve basically, our 68% are going to lie within 1 standard deviation, 95% of the observations will lie within 2 standard deviations, and 99.7% will lie within 3 standard deviations. So that, I mean, that's a big deal. You can tell exactly how much of your data is lying in a certain area based on the empirical rule if it's normally distributed, if it's a bell-shaped curve. Now, Chebyshev's rule, they give you a formula for figuring the observations within k standard deviations. So if you have a data set and you say, okay, I want to know how much it is between 2 and 3 standard deviations, as you see below. Take 2, put it in for k. Take 3, put it in for k. And you can solve it, and you see what the answers look like with the 2 examples you have below there. So that's what Chebyshev's rule says, but we're going to actually probably use the empirical rule more in this class. So that's section 3.2, standard deviation. Hopefully you've got your graphing calculator handy. You can check yourself very easily with the graphing calculator for standard deviation. Make sure you're doing that. If you have any questions, please ask your instructors.